and then I'll leave an even easier one for you to practice. So it's actually most difficult, less difficult, and least difficult. All right, notation-wise, primes are wonderful, but we want to write it as dy dx. So x cubed. This one's already in the most convenient form for a homogeneous differential equation. The issue is this form doesn't necessarily allow us to determine visually that it is homogeneous, right? Because it's not in the standard form for a homogeneous differential equation. So you're relying on the fact that I'm telling you to solve the homogeneous differential equation. I guess I didn't need to highlight all of that, just the homogeneous part, right? So when it's in this form, you need to have been told that it is homogeneous, otherwise you wouldn't necessarily know to use this technique. All right. So pulling it right off the previous page, maybe I'll just rewrite it. So we have y equals vx and dy dx, which I never memorized. It's because it's just a derivative using the product rule. So first times the derivative of the second, which would be 1, plus the second times the derivative of the first. So we have our substitutions. Left-hand side of the equation becomes v plus x dv dx. Right-hand side, we have an x cubed plus a vx cubed over an x times vx squared. All right, it's only the pre-calc that makes this challenging. All right, we're already ahead of the game on this problem because I didn't have to do any work to get it into the form that I like. All right, now when I clean up the right-hand side, x cubed plus v cubed x cubed over x cubed v or vx cubed, either way. All right. Now, just like the last one, and this is how it works. This is kind of the reason why we do this. You should get a cancellation, a nice cancellation on the right-hand side. If it doesn't happen, you start questioning whether you did it right. So dividing everything by x cubed gives us 1 plus v cubed over v. U. Because we're dividing each term by x cubed. So if you divide x cubed by x cubed.
Oh, it is 1.
Yeah.
Okay. See, I knew it was simple. I just couldn't see it.
But that made me start to double check what I was doing. This should have been v squared, and this should be v squared. Because something didn't feel right. And Teresa's not here to let me know. Which is always appreciated because she usually gets me before I get too far down the line. Because I had it once. I was teaching stat class. And I was going over standard deviation by hand with some like decimal values. It was like a crazy problem. It wasn't conceptually difficult, but a lot of calculations involved. I got like 45 minutes into the solution, and somebody was like, "Oh, I think you made a mistake." I was like, "Oh, where?" And they're like, "Oh, you just got to scroll up." I'm like, "Where?" I'm like, my heart starts sinking at that moment. I was like, "Wait. Like a little up or a lot up?" Oh, like in the beginning. And I didn't lose my mind, but I came as close as I could to professionally losing. I was like, so you're telling me that you waited for me to be done with the problem 45 minutes later after you noticed the mistake before you were going to point it out? Thank you so very much. And this is before like smartboards. So I grabbed the eraser and erased everything on the chalkboard. I was like, okay, So let's start that one over again. Thank you, so-and-so. And then we continued on our journey. And class ended 45 minutes after it should have. Oh, that frosted me pretty good. So, so it's always appreciated if you notice something. Definitely don't be shy. All right. So right-hand side is as simple as I can get it. Left-hand side, I got a little bit more maneuvering to do. I can subtract off the v. And that's the same as saying, if I multiply top and bottom by v squared to get my common denominator, it's the same as saying that we're subtracting off of v cubed from the top. I mean, that's beautiful. Because now we have x dv dx on the left-hand side, and just a 1 over v squared on the right-hand side. All right, the pre-calc is going to make our calc a lot easier. All right, so clean it up. X is to the left. I'm sorry, to the right. V is to the left. V squared dv would be equal to 1 over x dx. Integrate each part. All right, this is the first instance where we have to do some calculus. All right, 1/3 v cubed equals ln of x plus c. Always hang on to that absolute value until you have reason to let it go. In the last problem, all it took was knowing that we were raising to an even power, and that was the end of it. All right, if you don't have a good reason to let it go, then you got to keep it. All right, I'm going to multiply both sides by 3. And we get v cubed equals 3 ln of x plus c. Now v has to go. V is the same as y over x. There's no converting to exponential form or anything like that because I don't have a log on the left-hand side. So I'm just going to cube it out. And then cross multiply. So we're looking at y cubed is equal to, I'll write it as 3x cubed ln of x plus cx cubed. I briefly considered making this coefficient of 3 into the exponent for x. Just swinging it up like I did in the last problem. But I dismissed it as something that I wanted to do because that's not going to help me get rid of the absolute values. Because if you cube a negative number, it's still negative. So if that was a coefficient of 2, though, I would move it up, make it the exponent, so that I could drop the absolutes, right? But not the case here. So really the only thing I can do now is take the cube root of both sides. If I want to, I can pull out the x cubed. But since our goal is really to just get y alone, once we do that, I'm not going to get too hung up on the pre-calc stuff. You know, beyond that, I mean, you had to do plenty enough pre-calc to get to this point to begin with. So you can call this the final answer, or if you wanted to factor out your x cubed and take the cube root of it, you could say y equals x times the cube root of 3 ln of x plus c. And again, that absolute's there. You got to make sure that the domain considerations are accounted for, because you can't take the log of a negative number and you can't take the log of 0. All right? So this is protecting us from ourselves. Now, if they state a domain in the problem, if they say, given this differential equation where x must be greater than 2, for example, then you don't need the absolutes because x is naturally going to be a non-negative number. Right? But until you have some reason to get rid of those absolutes, you got to keep them. All right? And that's the #1 cause of error number one point deduction on a unit test is that people don't have absolute values when they should. And and I don't go looking for them. It's like, ha, you don't have absolute value there. You have parentheses instead. What are you, some kind of loser? No, it's not like that. It's more like because you didn't have the absolute values, you screwed something up down the line. And when you went to solve for the value of C, you got the wrong answer. So it naturally penalized you. It wasn't that I was going to look for it. I'm not that nitpicky. All right, so, but you can see this one's much easier than the previous one. Not easy by definition. I mean, when you fill up half a page of your notes with one single problem, you cannot then call that problem easy. All right, it's a contradiction of terms. But it's definitely, I think you would agree, easier than the problem that was on the previous page. All right, and so the problem that follows is actually even easier. So I don't want to deprive you of the opportunity to try that one on your own. All right.